7-segment displays aren't used very much for providing output with electronic circuits anymore. They're mostly relegated to things like electronic alarm clocks, bedside clocks, things like that. A few reasons for that, not least of which is of course they're rather limited in terms of the level of output they can produce. It's just numbers, whereas something like a liquid crystal display obviously lets you have a full alphanumeric output. Typically, a 7-segment display will have a common cathode or a common anode, and this will take 2 of the 10 pins. The remaining 8 are for the 7 segments plus 1 for the decimal place. Therefore, in order to fully wire up a 7-segment display, you need to connect 7 connections plus the anode or cathode. And that's an awful lot of connections when you start to add up to multiple digits. And typically, you'd probably use 3 or 4 of these in a given project.
Here's a 7-segment display connected in a simple circuit to a benchtop power supply providing 5 volts. The plus 5 volt rail is connected via a 220 ohm resistor to a fly lead. I apply this in turn to the anode connections of each of the 8 LEDs. The common cathode is connected to the circuit's ground. Now, if we want to use all 7 or even 8 LEDs at the same time, we need a separate resistor for each one. Running multiple LEDs in series with a single resistor will give us variable light output, and if we try and light all 7 segments at once, it would be very dim. If you want to use 3 7-segment displays, that means you need 21 resistors, and it's almost impossible to wire that neatly on a breadboard. If we were to wire 3 7-segment displays directly to a microcontroller, then we'd need 21 output pins, which is more than is typically available. Instead, I'm using 3 HEF4543 7-segment display driver chips. These take a 4-bit binary value corresponding to the digit 0 to 9 that we wish to display and set the appropriate state for the 7 segments. This means that we can use 12 pins from our microcontroller to give us 3 binary coded decimal digits. In order to demonstrate this, here's a simple, though unavoidably untidy Arduino circuit that will drive 3 7-segment displays, counting from 0 to 999 before rolling over to 0 again. Let's take a look at the source code required to drive this circuit. We start by setting the pin mode for our 12 output pins, digital pins 0 through 11. The main loop simply iterates through, calling the display function, adding 1 to the counter, checking if it's still in bounds, and then delaying for half a second. The more interesting part of the code is the display function itself. It takes as a parameter an integer value corresponding to the number to be displayed on the 7-segment displays. We need to convert this into 3 4-bit binary coded decimal digits. To store these, we have 3 variables representing the 3 digits, A, B and C, with C representing the most significant digit. We calculate the value for C simply by performing integer division on the value. Note that for this simple demo we assume that the value is in bounds, that is to say less than 1000, but it would be good practice to explicitly check this before proceeding. The middle digit is slightly more complicated to calculate. We perform modulo division by 100 to give us the remainder, the tens and units part of the number, and then perform another integer division by 10 to calculate the digit. Finally, digit A is simply the remainder when we divide the original value by 10. In order to avoid the need to latch the display whilst we set the bits individually, we're writing all of the bits simultaneously using the port registers corresponding to the 2 banks of 8 pins. Port B represents pins 8 through 13. Since we're using the least significant bits of that range, we can simply set the port B register to the value we wish to output. The port D register represents pins 0 through 7, and to use it we need to set 2 separate digits, A and B. To do this, we shift the more significant of the 2 4 places to the left, and then add the less significant bits to the result. And this gives us 8 bits containing 2 4-bit binary coded decimal values. Here's the output from the circuit. The display is counting up in half-second intervals. The LED 7-segment displays look good, and they're pretty simple and easy to understand, if you can avoid too much of a tangle with the wires. But realistically, they're not very practical for most users, and that's one of the many reasons why they've been mostly replaced by liquid crystal displays. Thanks very much for watching. See you next time.